Good afternoon, my name is Judith Balkissoon. This afternoon I will be presenting on unsteady magneto-hydrodynamic poiseuille flow through a porous channel under an oscillating pressure gradient and uniform suction and injection. This study was done under the supervision of Dr. Rao and Dr. Victor Job. This study has applications in chemical engineering, in agriculture, such as freeze-drying food products, heating up soil to enhance growth of plants, industries to help with lubrication of machinery with porous lining, in the petroleum engineering industry for flow of oil and gas production in wells, and in crude oil production. Magnetohydrodynamics is the study of the interaction of flow of electrically conducting fluids with magnetic fields. Poiseuille flow can be defined as fully developed laminar flow between two parallel stationary plates separated by some distance, driven by an applied pressure gradient. Brinkman's equation is the equation that was used in this study. It describes flow in porous media and is a combination of the Navier-Stokes equations and the Darcy equation. It shows the transformation from slow flow, governed by Darcy's law, to viscous free flow, governed by Navier-Stokes equations. The objectives of this study are to obtain numerical solutions for the velocity distribution of this flow and to determine how velocity is affected by Hartmann number, represented by HA, the frequency of oscillation omega, suction and injection parameter S, the permeability parameter alpha, time t, and the amplitude of the pressure gradient. To do this, the Galerkin finite element method was used to solve the governing equation numerically under the initial and boundary conditions. The weighted integral method was used for the spatial semi-discretization. The Crank-Nicolson scheme was used for the time discretization. The elements were assembled and MATLAB was used to solve the system of equations. This is a schematic of the physical system. The XY Cartesian coordinates were used. The x-axis runs along the middle of the channel and going vertically is the y-axis. This is the upper plate represented by y equal h, the lower plate y equal negative h. Uniform injection is applied at the bottom plate, uniform suction at the upper plate, and an applied magnetic field B naught is applied in the y direction. The velocity of each plate is equal to 0, so the plates are stationary. The governing equation is Brinkman's equation. Here, rho represents the density of the fluid. Del P del X represents the oscillating pressure gradient. V naught is the velocity of the suction and injection. Mu is the viscosity. Sigma represents electrical conductivity. V naught is the magnetic field, and K represents the permeability of the porous channel. The initial conditions, velocity equals 0 initially. The boundary conditions, each plate is stationary and each plate is positioned at y equal plus or minus h. The pressure gradient is represented by the expression negative A into 1 minus cos omega t, where omega is the frequency of oscillation and A is the amplitude. When non-dimensionalizing the Brinkman's equation, we get this equation where S is the suction injection parameter, HA is the Hartmann's number, alpha is the permeability parameter, and this represents the applied pressure gradient. When non-dimensionalizing initial and boundary conditions, the only thing that changes would be where y was equal to plus or minus h, y now becomes plus or minus 1. Results. Figure 2 shows the velocity profile for poiseuille flow for different values of the permeability parameter, alpha equals 0, 1, 2, 3. As alpha decreases, the velocity C is seen to increase. This occurs because a decrease in alpha, which is represented by h over the square root of k, where k is the permeability of the porous material. When there's a decrease in alpha, it means that there's an increase in the permeability of the porous material, and therefore the velocity increases. This is in good agreement with a study done by Verma Gupta in 2018. Figure 3 shows how the velocity profile is affected by different values of the suction injection parameter. So here, suction goes from 0, 1, 2, 3, suction injection parameter, sorry. At S equals 0, the graph seems to be symmetrical. However, at S not equal to 0, so at S equal 1, 2, 3, the graph skews towards Y equal 1. This Y equal 1 represents a plate where there is suction. So as velocity increases, the suction injection parameter decreases. Here, alpha is used as 0.00001, which means that the permeability of the porous material is high and therefore velocity increases. This result is also in good agreement with studies done by Verma and Gupta in 2018. Figure 4 shows the velocity profiles for varying values of Hartmann number. Hartmann number equals 0, 1, 2, 3. And figure 5 shows how time variation of velocity is affected by different values of Hartmann number. Both graphs show that Hartmann number decreases as the velocity increases. This occurs because a decrease in Hartmann number means that the Lorentz force acting in the direction opposite to the flow decreases. So as Hartmann number decreases, the magnetic damping force decreases, and therefore velocity increases. This result is in good agreement with work done by Magnon, Kiyama, and Iyaya in 2012, Monier, Manhassanen in 2013, Verma and Gupta in 2018, and Gupta and Jain in 2016. Figure 6 shows the profiles of velocity for POISEUILLE flow for different values of frequency oscillation. It is seen that the frequency of oscillation decreases as velocity increases. This may be because the pressure gradient, the expression used for pressure gradient is A into 1 minus cos omega t, where A is the amplitude of oscillation. So as the frequency of oscillation decreases, the pressure increases, which causes an increase in velocity. Figure 7 shows the effect of frequency of oscillation on time variation. It shows that as the frequency of oscillation decreases, the velocity also decreases. This is because at a lower frequency, fluid flow slows down. This is according to notes by Nakayama and Boucher. In figure 8, the effect of variation of amplitude on time variation is shown. It can be seen that as the amplitude increases, the velocity increases. This is because pressure increases as amplitude increases, and hence velocity increases. Figures 9, 10, 11, and 12 all show the effect of alpha, which is the permeability parameter, S, suction injection parameter, Hartmann number, and omega on time variation of Q, which is the volumetric flow rate. As alpha, suction injection parameter, and Hartmann numbers decrease, the volumetric flow rate is seen to increase. So when alpha is 10 and it decreases to alpha equals 0.0001, the volumetric flow rate is seen to increase. And the same thing happens with suction injection parameter as well as Hartmann number. This result is in good agreement with a study done by Schick and Roy in 2012, which found that when an external magnetic field is applied to a system, the volumetric flow rate decreases. Figure 12 shows that as the frequency of oscillation increases, so does the volume flow rate. In conclusion, the velocity increases when the permeability parameter, suction injection parameter, Hartmann number, and frequency of oscillation decrease. The velocity increases when the amplitude of the pressure gradient increases, and the volumetric flow rate Q was observed to increase as the permeability parameter, suction injection parameter, and Hartmann number decreased, but it increased as the frequency of oscillation increased. These are some of the references I used in this study and which are in particular in the slides. Thank you for listening. Any questions?
Okay, so thank you very much for a good presentation.
Thank you.
Do we have, just will check, do we have any questions in our chat? Do we have any questions? Is someone ready to ask? Okay, so then I will ask a simple question probably. What could be practical applications? What do you think about how is it possible to use your nice modeling results in practical applications?
It could be used in, I see the most use in the petroleum engineering industry. For example, with the flow of crude oil and oil and gas and so on in oil production.
Okay, so then, but in this case, scaling problem could become very important if you want to affect
Yes.
flow in rocks. Okay, but from that standpoint, modeling, yeah, modeling work is important because if you have nice model, scaling is not a very difficult problem. But then you need to solve a problem in three-dimensional approximation.
Yes, further work can be done.
Okay, very good.
Thank
you very
you.
much again. And I think that anyone could who wants can send questions to